Hello students, welcome to Inside Physics. Here we see what is a toroid. See, this is another shape of a solenoid. A solenoid, there is so many number of turns of a conductor which are wound on a metal rod or another better conductor. So, if you wound some turns of a wire or conductor and the turns are in circle shape, it appears as circle, but actually they are not circles, they make a shape of a helix. So this solenoid shaped system is bent into a circular system. When it is bent like this, that means when you are taking the turns, the number of turns on a circular shaped metal rod, the turns will be like this. Okay, and this will continue around all the metal rod. So actually we have bent the solenoid into a shape like this, and these turns are actually connected to a voltage supply. That means a current must be passed in these coils. Okay, so what is the difference between the solenoid and a toroid? And we see the concept of toroid here. See, when you actually see this toroid, the sectional view of this toroid, I have given the sectional view. What are the sections? Here there is a section inside the toroid and outside, and in between the coils there is one more section. So we have divided this toroid into section 1, section 2, section 3. So we actually get some magnetic field around a solenoid and inside and outside, and here also for the toroid we also calculate the magnetic field in and around the toroid and actually inside the coil. So by calculating the magnetic field, we actually feel the difference between solenoid and toroid. So we know for a solenoid the magnetic field will be mu naught n I. Okay, so inside the solenoid, and here mu naught is the permeability of free space, n are number of turns per unit length, and I is the current flowing through the coil. So here we also calculate the, see, in the same way the magnetic field will be calculated for this toroid. First of all, we see the dotted circle 1. This means to calculate the magnetic field, we are actually using Ampere's circuital law. What does it say? Is equal to mu naught I. So by this we can write it as mu L mu naught I, where L is the perimeter of the Amperian loop. To calculate the magnetic field, we actually consider a loop called Amperian loop. By that we will calculate the magnetic field on that loop. So here if you observe, this is the dotted cross symbol where the magnetic field is going into the board. This is the dot symbol where the magnetic field is coming out of the board. So here the solenoid turns are like this. So when you consider the turns like this, and by right hand thumb rule, when you actually put the finger around this loop, the magnetic field is denoted by the curled fingers. So if this is the coil, I will put the right hand thumb rule like this, and the magnetic field is taken going into the board in here and coming out of the board here. Okay, so this is the magnetic field we imagine here, and the current loop, actually here take this as the loop and we put the thumb as here. So in this Amperian loop, if you observe, there are no currents passing or come into the board or coming out of the board inside this loop. What Ampere's circuital law says, the magnetic field will be calculated only if the currents are passing inside the loop, whether they are coming out or in, they must be inside the boundary of this loop. If you observe, this is the this is where the current is passing and there is no current inside this loop. We can say for this Amperian loop 1, the magnetic field is 0. Okay, because there are no currents here inside this loop. And we will take the third loop. For the third loop here, this one is the third loop. Actually, there are currents going in and out inside this loop. This is the third loop, the last one, and inside this loop there are definitely some current going into the board and out of the board. Like this is a coil of the toroid, and if you observe, the current is passing in and there the loop will be here. The third loop, what we have considered is like this. So covering all the toroid and the loop is outside the toroid. So inside the loop, what is happening? If you observe inside this third loop, the number of currents going in and coming out are same, because if you observe single loop, the loop is carrying a current in a clockwise or anti-clockwise. So inside this loop, the number of currents passing in and out. So as per Ampere's circuital law, the algebraic sum of all the currents going in through the boundary or loop are actually is equal to 0. So the sum of all the algebraic sum of all the currents means if I comma I1 comma I2 are going in, they must be actually cancelling with I3 and I4, where I1, I2, I3, I4 are same values. So if all the same number of values going in and number of values coming out, mixing all together because of the sign, one is going in and other is coming out because of the sign, the algebraic sum of all the currents will actually come is equal to 0. Then by this relation, the magnetic field for loop 3, this loop, is 0. So by these two conclusions, 1 and third loop, we can say inside the toroid the magnetic field is 0, outside the toroid, that means here the magnetic field is 0. What about inside this toroid? Inside this toroid, inside means not here, inside between the coils. So this is the Amperian loop we have considered between the coils. So this loop actually contains some current. So right, so this is the radius. If you consider this second, the number 2, what we have given for this loop, this is a spot S on the loop 2. Loop 1, this is actually loop 3, and this is considered as loop 2. On the loop 2, which is going through the coils, the spot S where we calculate the magnetic field will be actually tangential to this loop. The magnetic field everywhere on this loop is tangential. That means when you draw a tangent like this at this point S, that is the direction of the magnetic field. So how the magnetic field is calculated on this loop means, if you consider this radius as R, okay, and this magnetic field, see the current flowing here inside the loop. You consider inside the loop there are some currents going in or out only in one direction. We are not considering the entire toroid. We are only considering this amperian loop, and inside this loop the current direction is only in one direction, either outward or inward. So here the current will be flowing in one direction, so there is a definite sum of current passing through the loop too. Okay, then here we calculate the circuital law as per Ampere's circuital law. We can say that B into 2 pi R is equal to mu naught. So the number of turns, the total number of turns of the solenoid, if it is n, we can put it as mu naught ni. So if n is equal to, we can write n is equal to n into 2 pi r, means number of turns per unit length into perimeter of the amperian loop. So by this we can write mu naught n into 2 pi r into I by 2 pi r. So by this we get magnetic field inside the toroid is nothing but mu naught ni, which is absolutely represents equivalent to the magnetic field due to a solenoid. We also get the same result for the solenoid also. So there are some similarity. By calculating the magnetic field, we got the same value as the solenoid. But in actual circumstances, there will be some magnetic field, little magnetic field outside and inside, where we actually supposed to have taken as 0 at loop 1 and loop 3. But in realistic conditions, the magnetic field will be very slightly present. Okay, so this is the concept of toroid.